In this lesson, we're going to look at several reactions of substituted benzenes. We'll be looking at substituent oxidations and reductions, nucleophilic aromatic substitution, and benzyne intermediates. First up, we have benzylic oxidation. Most alkyl groups attached to a benzene can be oxidized to give a carboxylic acid. The reaction is often performed using acidic sodium dichromate. In the first example, we see toluene being oxidized to benzoic acid. It's important to recognize that only benzylic carbons are oxidized, and only those that have at least one hydrogen attached. If we look at this example, we see that the benzene has 3 benzylic carbons. However, only 2 of these benzylic carbons have hydrogens attached. The methyl carbon on the top and the methylene carbon on the right are both oxidized to a carboxylic acid. The tertiary benzylic carbon on the left remains unchanged. One particularly useful reaction of substituted benzenes is benzylic deoxygenation. Benzylic aldehydes and ketones can be deoxygenated under acidic or basic conditions to give alkylated benzenes. The first example shows a Wolff-Kishner reduction. Here we see acetophenone reacting with hydrazine under basic conditions to give ethylbenzene. The same transformation can also be achieved using the Clemmensen reduction. In this example, we see acetophenone reacted with zinc-mercury amalgam under acidic conditions to give ethylbenzene. You may be wondering why we have 2 different reactions that actually accomplish the exact same transformation. Having multiple methods of accomplishing the same type of reaction is actually really important. In this case, the Wolff-Kishner reduction and the Clemmensen reduction complement one another with respect to pH. The Wolff-Kishner reduction requires strongly basic conditions, while the Clemmensen reduction requires strongly acidic conditions. Performing a Wolff-Kishner reduction on a molecule that had other base-sensitive functional groups would likely result in the formation of undesired products. Performing the same deoxygenation using Clemmensen reduction conditions might be more prudent. Benzylic deoxygenation is a very powerful synthetic tool when used in conjunction with the Friedel-Crafts acylation. The tandem reaction sequence of Friedel-Crafts acylation and deoxygenation is a convenient source of alkylated benzenes. In the example, we see benzene acylated with a 3-carbon acyl halide. The resulting ketone can then be deoxygenated to give propylbenzene. This might at first seem like a roundabout way of introducing an alkyl group to a benzene. Why not just perform a Friedel-Crafts alkylation? Well, there are 2 major problems with Friedel-Crafts alkylation. Remember that with most primary alkyl halides, Friedel-Crafts alkylation is prone to rearrangement, which typically prevents the introduction of straight-chain alkyl groups to the benzene. The other issue is that the newly introduced alkyl group is an activating substituent. The product is more reactive than the initial benzene in the Friedel-Crafts alkylation reaction. This can often lead to multiple alkylations occurring. The alkylated product simply reacts more quickly than benzene itself. Tandem Friedel-Crafts acylation and deoxygenation solves this problem. Friedel-Crafts acylation is not prone to rearrangement, and the newly introduced carbonyl group is a deactivating substituent. This makes the product less reactive than benzene. The Friedel-Crafts reactions typically fail on deactivated benzene rings, and that means the Friedel-Crafts acylation almost always occurs only once. The next reaction is the reduction of a nitro group. Nitrobenzenes can be reduced to anilines. The reaction can be achieved using tin metal under acidic conditions or with classic hydrogenation conditions, using hydrogen gas and palladium on carbon. Aniline is an extremely useful compound, particularly in the dye industry. The reduction of a nitro group provides a simple, cheap way of making aniline. The starting material, nitrobenzene, is itself made using very inexpensive nitric and sulfuric acids. The next reaction we're going to explore is nucleophilic aromatic substitution, or SNAR. SNAR is, not surprisingly, a variation of nucleophilic substitution, like SN1 and SN2. In the SNAR reaction, a leaving group, typically a halogen, is replaced with a strong nucleophile. The reaction usually requires a strong electron withdrawing group be present either ortho or para to the leaving group. So in the example, we see para-chloronitrobenzene reacting with a generic nucleophile to initiate the substitution. Typical nucleophiles include hydroxide, alkoxides, and amines. If we look at the mechanism, we can see why the reaction requires a specific placement of an electron withdrawing group, typically a nitro group. In the first step, the nucleophile attacks the electrophilic carbon bonded to the leaving group. Because the leaving group is attached to an sp2 carbon, both SN1 and SN2 mechanisms are forbidden. Rather than displacing the leaving group directly, the nucleophile breaks the carbon-carbon pi bond attached to the electrophilic carbon. This results in the formation of a resonance-stabilized carbanion, often referred to as the Meisenheimer complex. If we look at the first three resonance structures, we can see that the negative charge ends up in the positions ortho and para to the site of nucleophilic attack. Placing a group that removes electron density from the ring via resonance allows a fourth resonance structure to be drawn in which the negative charge is placed outside of the ring. In this case, the fourth resonance structure places the negative charge on one of the oxygens of the nitro group para to the leaving group. This greatly stabilizes the Meisenheimer complex, making the reaction kinetically feasible. In the second step of the mechanism, the lone pair pushes back towards the electrophilic carbon, reforming a pi bond and displacing the leaving group. Nucleophilic aromatic substitution is one way of introducing substituents to the benzene ring that can't be incorporated using EAS chemistry. We'll wrap up our initial look at the reactions of substituted benzenes with a brief introduction to benzyne intermediates. As you can probably deduce from the name, benzyne is simply a benzene in which one of the double bonds has been replaced with a triple bond. If we look closely at the two carbons on the right that are involved in that triple bond, we can see that those carbons are sp hybridized. Remember that sp hybridization means linear geometry, bond angles of 180 degrees. But in benzyne, those bonds are distorted into roughly 120-degree bond angles. This makes benzyne extremely unstable. It's a reactive intermediate and cannot be isolated. Benzynes can be formed via an elimination reaction. As you can see in the example, treatment of a halobenzene with a strong base, in this case sodium amide in liquid ammonia, forms a benzyne intermediate. In the absence of any other reagents, the initially formed benzyne intermediate often undergoes an addition reaction with ammonia to give an aniline. The addition of ammonia to benzynes can be a synthetically useful route to substitute in anilines. In this example, 2-chlorotoluene is treated with sodium amide in liquid ammonia to give a benzyne intermediate. The presence of the methyl group in this intermediate desymmetrizes the triple bond. Ammonia can now be added across the pi bond to give two different regioisomers. The two products are referred to as the direct and kyne regioisomers. The direct product places the nitrogen on the same carbon originally attached to the leaving group. The kyne product places the nitrogen on the carbon adjacent to the carbon that initially was bonded to the leaving group. The word kyne shares a root with the word kinetic, both meaning movement. In the kyne product, the nitrogen moved to the carbon adjacent to the leaving group. The overall mechanism is pretty straightforward. In the first step, the sodium amide removes a proton from the carbon adjacent to the leaving group. The resulting carbanion pushes electrons towards the adjacent electrophilic carbon, displacing the halogen and forming the triple bond. In the next step, the benzyne acts surprisingly like an electrophile. The strongly nucleophilic NH2- can attack either of the two electrophilic carbons of the benzyne triple bond. In this case, following the green curved arrows, the nitrogen attacks the top carbon of the triple bond. The resulting carbanion is then protonated by ammonia to give the kyne product. Similarly, following the red curved arrows, the amide attacks the lower carbon of the benzyne. Once again, the resulting carbanion is then protonated by ammonia, now giving the direct product. The formation of both direct and kyne products is strong evidence that the reaction does not proceed through a simple SN1 or SN2 substitution. Only through the formation of a benzyne do we see electrophilic character shared over two adjacent carbons. The regioselectivity of the reaction, that is, whether the kyne or the direct product is favored, is influenced by both steric and electronic effects and is beyond the scope of this lesson.